This video covers vectorized functions in R. So we are talking about trying to write more efficient code. So trying to maybe root out redundancies and save some time for you. And so we talked about the idea of doing for loops. If I have something that I'm doing, say, more than 3 or 4 times, I usually want to make that into, say, a for loop so I don't have to continually rewrite that same chunk of code. But for loops are kind of inefficient in R. And so let's just briefly talk about why. R is an interpreted language, which just means that it's doing a lot of the overhead for you. So whenever you say mean of this vector, you're not telling R whether or not that vector is an integer vector or whether or not it's a double vector or whatever. R is going to figure that out on its own and then apply the appropriate method. So R is doing essentially a bunch of extra things under the hood to make your life easier. And so if you do a loop, every time that it goes back to the top of the loop and then goes to execute that same chunk of code, it has to go through the same process with each line of that code to determine, well, oh, this is a numeric thing. I'm going to go ahead and do, and it's integers only, so I'm going to go ahead and do this kind of evaluation. And so that overhead just sort of slows down the computations. And so there's the idea of doing what are called vectorized functions, which are much faster. So essentially, these functions just act on an entire vector or matrix or whatever else you want to call it. Okay. And so we'll see some examples, and then we'll also actually compare the speeds of them to see that they are indeed faster. Okay, so there are some built-in vectorized functions that are really, really useful. So in the last video, we talked about finding the summary statistics for each column of a data set. Well, there are built-in functions to do just say column means. So col means and row means will go through a matrix and grab and calculate the mean of each one of those columns. And these are vectorized functions, so they're going to be very, very fast. There are corresponding functions called col sums and row sums. And then if you install and read in the matrix stats package, there are col SDs, col vars, and col medians. So basically all of your simple functions simple summary statistics that you want to grab, there are vectorized functions that you might want to use for those. We've also looked at a vectorized function already called ifelse, which is the vectorized version of the if-then-else logic. And we're also going to talk about the apply family of functions. So we've briefly talked about tapply earlier. And these are not truly vectorized functions, but they're pretty close to it, and they run really fast, especially as compared to for loops. And lastly, you can actually create your own vectorized functions with the function called vectorize. So you would write your function that evaluates for a single argument, and then vectorize will make it so it will work for an entire vector. Okay, so let's just see how to use some of these built-in functions to sort of do things more efficiently. So let's deal with this batting data set. And so we have this col means function, and basically what it requires is just a numeric data frame, which means it's just got to be an array. So everything in it needs to be numbers. And so I might take that batting data set that we were working with previously from the layman package and just grab the columns from games to ground it into double plays. So all the columns in between here and there are numeric. So I'm using select from dplyr. And so just col means on that, and then I'm removing any NAs. And so it outputs the mean for each one of those variables. Okay. And so what we could do is compare the computational time it takes to do this via looping versus do this via the col means function, a vectorized function. So there's this package called micro benchmark. And micro benchmark is for, so benchmarking is whenever you're sort of testing out your program and seeing how long it takes to run. Micro benchmark is for the case where your program is maybe pretty small. And so you don't want to just run it once, but maybe you want to run it like 100 times and then get the average or summary statistics about the runtime. And so this will essentially do all of that for you. So we'll install that package. We'll read it into our session. And all we need to do to do the benchmarking is wrap the code that we want in this micro benchmark function. So I'm going to do my selection outside of the col means statement so that it doesn't slow down my computation. So I'm going to select just the columns I want. I'm going to micro benchmark the running of this code that you see here. And so you can see that in milliseconds, this thing evaluated 100 times. That's the default for micro benchmark. So it evaluated that code 100 times, and the average milliseconds it took to evaluate the call means line of code was about 6 milliseconds. And the median time was 4.8 or so. Correspondingly, I could go through and do this with looping. And so here I'm doing a loop that loops through the corresponding columns. So there's 17 columns. And I'm finding the mean for each one of those columns, removing the NAs. So also reported in milliseconds, we can see that the mean was about 20 milliseconds, median also right around 20. You can see that the vectorized function is in fact quite a bit faster. Of course, it doesn't really matter for something this small, but if you're trying to scale this up to a larger analysis, this kind of thing is important. Okay, and one nice thing about vectorized functions is that since they work on, say, an entire matrix or entire vector, is that you can get some really cool stuff pretty easily. We've already kind of seen this a little bit through what we can do with dplyr, but we could find the median number of games, at-bats, and home runs for all players. And so the idea here would be, let's group the observations by player ID, because there are multiple entries for each player if they played more than 1 year. We want to summarize the variables that we care about, games, at-bats, and home runs. And we're going to need to remove non-numeric columns so that we can run, say, call means, or call medians in this case. Okay, so that'll be our steps. Group them, summarize, get rid of the numeric stuff so that we can then just apply call medians and get our results. So here we go. We're going to use the chaining. So we're going to take the batting data set. We're going to group it by player ID. And then we're going to find summaries. We'll find the total games, total at-bats, and total home runs for each one of those players. And now we'll go ahead and get rid of the player ID column because it's not numeric. And then we'll coerce the result to a matrix so that we can use it within call medians and get the median number of games played for players across all of baseball history, median number of at-bats for all players across baseball history, and the median number of home runs. So again, getting down that logic is the hardest part. Now we have these vectorized functions. Things will go very, very quickly for your computations. All right, another place where we might want to use these vectorized functions is creating new variables. And we've actually already done this, but just give you another example of it. So there's a built-in data set called air quality. And this gives air quality measurements in New York City from back in the 70s. And so there's a column called ozone, solar radiation, wind, temperature, month, and day. Okay. And so what we might want to do would be, say, create a wind category variable. And so we might define the categories for this wind variable as you see there. So a high wind day would be if the wind was greater than or equal to 15 miles per hour, a calm day if it's less than or equal to 6, so on and so forth. And so, one idea would be to loop through every one of these wind values, check the if conditions that you see here, and assign the appropriate value to the new variable. Okay, so that might be your initial thought. When I first started doing programming, I had learned C, and so my first thought always went to a for loop for something like this. Let's loop through each one of these observations, do my if then else, and determine the wind status. So here's how you might do that. Okay. I'm going to initialize a vector to save my new variable in. And I'm going to go for I in sequence length of the number of rows of air quality. So this is going to be basically 1 to the number of rows. I'm going to go through here and run this if else logic. If my wind is greater than or equal to 15, I'm setting my status to be high wind. If it's now greater than or equal to 10, set it to wind, 6, light wind, 0, calm. And then we have this catch-all category that basically if there was some mistake in my air quality, in my wind measurement, I should then see an error as my value. So that might be a perfectly logical and reasonable way to do it, and you'd get the right answer here. So the status variable now has the corresponding categories that we want. What we would do next is we would just append that to our data set. So since data frames are truly just lists, right, I can just create a new a new name for that list. So this is going to be a new entry. As long as it has the same number of rows or the same length as all the other columns, we're going to be fine with doing this. So I'm creating a new column that is status. And now I could find the mean temperature for each wind status, for instance. So that might be something I want to do. So I group by my status now, and I create a new variable that we're going to append to the data set since we're doing mutate, which is the average temperature. So on the status variable here, every time that there's a light wind, we're appending on this new average temperature variable. Okay, so we know that loops aren't great. So is there an what's the alternative way to do this? And this is the one that we've already seen before, the if-else, right? This is a vectorized version of the if-then-else logic. And so the syntax for it, we give it the vector of conditions, what to do if it's true, what to do if it's false. So the hardest part here will be writing out the vector of conditions. And really what we can do here is actually nest our if-else statements. So here I have, if this column is greater than or equal to 15, put high wind. So this is what you do if it's true. If it's false, do another if-else statement where we compare everything in that column to being greater than or equal to 10. And then if that's true, put windy. If it's not, do another one that's light wind. And lastly, if everything's false, do calm. So we don't have the catch-all category here, but that's fine. And so we might do some comparisons of our for loop speed versus our vectorized version speed. So here we're just wrapping the for loop that we were doing in this micro benchmark function, and we're saving that as loop time. Doing the same thing here, grabbing this if-else statement, wrapping it in the micro benchmark function, saving that as vector time. And so we can look at the summary statistics. Each one ran 1,000 times, and the mean time it took the loop to run was almost 10,000 microseconds, whereas for the vectorized version, it was 122. So a marked improvement there. Okay, so again, though, all of those sort of built-in vectorized functions are super useful, and you should utilize them if appropriate. And then there's this entire other set of functions that are referred to as the apply family of functions. These aren't exactly vectorized, but they're pretty close, and they're way faster than for loops. So let's talk about apply. Help for apply. Oops. So what does apply do for us? This returns a vector or array or list of values obtained by applying a function to the margins of an array or matrix. So by margins, they mean either to the rows or to the columns, or et cetera, if you have multiple dimensions. So I might want to say apply the mean function to each one of my columns. So right, that would be applying a function to one of my margins. And so apply basically takes in the array or matrix that you want to apply the function to. Margin defines whether you want to apply it to the rows, columns, third dimension, fourth dimension, etc. And then fun is the function that you want to apply. Okay. And so for margin, if you think about a matrix, which is what we're usually going to be dealing with, we do the dimensions of the matrix are rows by columns. So margin equal 1 is the rows because that comes first. Margin equal 2 is the columns because that comes second. So again, we have our data, which is usually a matrix. Margin, 1 or 2, 1 for rows, 2 for columns. Fun, the function that we want to apply to each one of those margins. So whichever margin we chose. And so we refer to the apply family of functions because there are multiple ones that are similar. So there's sapply, lapply. So we'll look at examples of those in just a moment. So we can go back to our air quality data, and we can consider finding, say, the summary statistics for each one of the numeric columns of interest there. So with apply, we need to specify those three things. First, the data set that we want to work with. So here, X is going to be just the columns from ozone to temp from the air quality data. I want to apply my functions to the columns, so I'm going to put margin equal 2. The function that I want to apply to each one of my columns is the summary function, which remember gives us the 5-number summary and the mean. And then if you go back and look at the help here, notice that there's the ... there. So that's where we're allowed to give unnamed arguments that would be, say, used in the function that we put here, right? So ... are optional functions that could be used in fun. So the summary function itself has an na.rm option. So I'm just going to go ahead and specify that afterward to say that this should be fed into summary. And so the really nice thing about doing this with the apply function is that it keeps the labels for the columns and reports it in a nicer way than when we did it with the for loops. So now we see for the ozone column, here's the summary. For the solar column, here's the summary. And so just a nice way of printing that out. Okay, so that's basic apply, which applies a function to rows or columns of a matrix. There are other apply functions like lapply. The L is out front because it stands for list apply. So applying a function to each element of a list. And this is something that comes up quite a bit, actually. So first, let's just obtain a list object that we might want to deal with. So the LM function fits a linear model. So we're going to just basically do a simple linear regression here between ozone and wind from the air quality data. But we're saving the output of that in this fit object. And so the output of this object actually it's actually a list, right? So that our functions generally return named lists. And so I'm just going to grab 3 of the things from that outputted object and put them in a list. And I'm just going to overwrite the fit object. Okay. So basically what you need to get out of this is that we have a list object called fit. It has 3 elements in it. Elements are residuals, effects, and fitted values from our linear model fit. And so what we might want to do with this list object, we might want to apply a function to each one of its elements, right? And so to do that, we can use lapply. Just to show you what fit looks like. So here's the first element of fit. It's a vector. The second element is another vector. And the third one, I think, is also a vector. Essentially, we have the same type of element in each one of those. And so we might want to find the mean of each one of those list components. And so lapply is similar to apply, but remember that lists are one-dimensional. And so since lists are one-dimensional, I don't need to say a margin, right? I just need to give it x, the list of interest, and fun, the function I want to apply to each list element. There's no margin to even worry about. There's no rows or columns. Lists are one-dimensional. So I lapply to my fit, which is my list, the function mean. So it returns a list. Here's the first list element. It's the mean of the first thing from fit. Here's a second list element it returns. It's the mean of the second list element. So lapply is super useful. Whenever you start dealing with sort of more varied data, you end up dealing with lists quite a bit. And so lapply is wonderful for dealing with those. There's a very similar function called sapply. It does the exact same thing that lapply does, except it tries to simplify what it returns. So it tries to return a vector if possible, for instance. So here, instead of returning a list with 3 things, it's returning a vector with 3 elements. So running sapply is essentially equivalent to running lapply of whatever you're doing and then running unlist on that. So unlist will take a list and just unlist it into a vector, if possible. Okay, and so let's just do a comparison of apply versus, say, call means, because like I said, apply is not truly vectorized. It's fast, but it's not as good as these vectorized functions. So let's compare using apply to using call means, just to see the difference there. So we'll do selecting of our ozone today columns from the air quality data set. We'll apply to that selected data to each column the function mean. And we're going to run that 100 times. And on average, it took 150 microseconds. Compare that to using call means on that same data set. And on average, it took 75 microseconds. So again, truly vectorized functions work much faster. Apply functions are pretty quick though, much better than for loops. Okay, so just be on the lookout for places where these types of functions can be used instead of, say, for loops. Anytime you go and you're thinking, I'm going to do a for loop for this, think if there's a way to do it in a vectorized form instead.